chapter 3 is? No, not at all. What do you think it is? Do you even care?
Polynomials.
We did polynomials. That was last chapter.
Polynomials on...
We're going to do something that we did already in Algebra 2. And maybe some of you liked it, maybe some of you didn't. But we're going to do a whole chapter on exponents and logs. Logarithms. Sam loves them. Look at him. He wants out. He was actually trying to climb through the window there. Did you see that? It's not going to work, Sam. Okay, I've tried it. Seriously. Okay, we're going to do exponents and logarithms, but no one ever says logarithm. We just say log. All right, so here we go, 3.1. Today, we're not going to do any logs yet. We're going to focus on, I just call them expos for short. We're going to do some exponential functions, and we're going to do something that you didn't do last year, which are called logistic. Different than log, but we're going to do some logistic functions too. So expos and logistic today. A lot of this is done without your calculator, and then it's kind of half and half. Okay, here we go. First part. Part A. Let's talk about, we have A, B, and C, and D. We got a lot to do. Let's go. All right, let's talk about exponential functions and what it means to be an exponential function. So first of all, an exponential function is a function. Okay, it's in the name. That means it passes the vertical line test. Exponential functions are actually one-to-one, so they pass the horizontal line test too. Let's go ahead, and this is what an exponential function looks like. F of x is equal to a times b to the x. Okay, this is not to be confused with a polynomial. A polynomial's exponents are numbers, 2, 3, 4, 5. Okay, exponential function, the exponent is the variable. So a is going to be our initial value, and b is the base, and b is not equal to 1. Okay? So exponential functions, we're going to do things that are either growing exponentially, like the population of a town is growing at a rate of 2%, or you won a game show and you double your money, you invest it and double your money every day, stuff like that, you know. Exponential decay, exponential growth, these things are all things you've heard of before. So let's go ahead and start with number 1. We're going to identify, ID, the exponential function. So we're going to say whether or not it actually is an exponential function, okay? And we'll just talk about what its initial value is, what its base is by looking at it, if it is an exponential function. So let's do a few. Here we go. Suppose I have f of x equals 5 times 3 to the x. 5 times 3 to the x, okay? This is not to be confused with 15 to the x. That is not true. It's 3 to the x and then times 5, okay? Because you have to do exponents before you do multiplication. So this one right here, is an exponential function. Yes, it is. The initial value is 5, and the base is 3. So maybe this is something where you got a terrible disease, and you have 5 terrible cells, and they're tripling every day or something. How awful. We should have come up with something nicer, like there's 5 rabbits and their population is tripling. Okay, that's gross though, because then, you know. All right, part B. Here we go. Let's do this one now. G of x is equal to 6 times x to the negative 4. Is that an exponential function? No. But you're like, wait, there's an exponent there. Doesn't matter. That's not even a polynomial. This right here has an exponent of negative 4. For an exponential function, our exponent needs to be the variable. So that we know. Okay, letter C. Let's do this. H of x is equal to negative 2 times 1/2 to the x plus 3. All right, this one's a little trickier because I added that plus 3. If I didn't, it would have been pretty easy to tell. This one, yes, it is an exponential function. Doesn't quite look like the one before, but it's just been shifted 3 up. And then if you wanted to find the initial value is not -2. Okay, this one's a little trickier. The initial value happens when x equals 0. Okay, that's our initial value when x equals 0. So if I were to plug in x equals 0 and simplify that, I wouldn't get -2. Can you do that in your head? Do you remember what anything is to the 0 power? It's 1. It's 1 times -2 plus 3 equals 1. All right, good. How about this next one? G of x is equal to 3 times 6 to the pi. Is that an exponential function? No, it's not. Pi is a real number. Pi is not a variable, so that would be no. Do you know what this is? What is g of x equals 3 times 6 to the pi? Anyone know? That's a constant. 3 times 6 to the pi is a number, right? 6 to the pi, it's going to be pretty big, times 3. This is just a horizontal line. Isn't that silly? It doesn't look like it, huh? Okay, and then let's do one more. One more of these. How about m of x equals 7 times 2 to the -x. Now, it's very tempting here to be like, nope, that's a -x. It's not x. But you know what? That doesn't matter. You can actually change this. This is the same thing as 7 times 2 to the -1 to the x. Do you agree with that? Because remember, power is raised to power, you multiply. And do you remember what 2 to the -1 is? 1/2. And so look at, there you go. The base is 7, or I'm sorry, the base is 1/2, the initial value is 7. Okay, so that's identifying what's an exponential function, all that stuff. And now let's go ahead and do some. So number 2, you might want to get your calculator out for this, but let's say that you have f of x equals 2 to the x. And these are going to be pretty easy for you. You might even be able to do a lot of these in your head, but they want you to evaluate. What is f of 4? F of 4. Do you know when you learned exponents? I think it's 5th grade, because my son just started doing exponents. It was because he took like a factor tree, and the factor tree was like 3 times 3 times 2. So they wrote it as 3 squared. And I was like, ooh, you're doing exponents. I was so excited for him. He wasn't. Okay, so this is 2 to the 4th. And we all know 2 to the 4th is 2 times 2 times 2 times 2. And the answer is 16. Very good. All right, let's do another one. Let's do f of -3. F of -3. So we're going to go 2 to the -3, and you might have to do this without your calculator. 2 to the -3. Remember negative exponents? Yes, they drop it down to 1 over 2 cubed, which is 1/8. Yeah. Okay, logs and exponents go hand in hand because an exponent actually, or a log actually is an exponent. So the whole chapter is on exponents and logs. They're inverse functions of one another. All right, let's try this next one's going to be a little harder, and it's something that you haven't seen, but let's see if we can figure it out. Here we go. All right, it's going to be a table of values, and suppose that we have our x values are -2, -1, 0, 1, and 2. Okay. And now I'm going to have 2 functions. I'm going to have function g of x and function f of x. And let's say that g of x, these values are 4/9, 4/3, 4, 12, and 36. And then let's do f of x. These values at -2, we get 128, and then 32, 8, 2, and 1/2. Okay, these are separate functions. We're not going to combine them together. But what they want us to do is they want us to find a formula for f of x and g of x. Okay? F of x and g of x. So to find a formula, there's a few ways to do this. What I like to do is just look for a pattern. Okay? So let's do, oh, I should have written them the other way, huh? Let's do that. Let's just do them in order. Sorry. Let's do g of x first, since that one's first, and then f of x. My bad. All right, so let's go ahead and do g of x. So it looks like g of x. Do you see a pattern, what's happening every time from here to here? What are they doing? Multiplying by 4. 3. 3. I looked at that 4 and I said 4. They're multiplying by 3 each time. Okay? So that would be, do you guys remember arithmetic and geometric sequences? Remember arithmetic, add a number each time, geometric, multiplied each time? And it ended up being an exponential function for geometric. We're going to do some more of that this year too. Okay, so your initial value, so we know that our base is going to be 3. Where am I going to write that? Right here. Our base is 3, and our initial value is what? Well, our initial value happens to be when x is 0. So what is our initial value here? 4. Okay, so let's write our equation. G of x equals 4 times 3 to the x. You don't have to put in parentheses. I kind of like to sometimes, just to remind me that it's 3 to the x times 4. And then you can test a point. Let's test x equals 1. If I plug 1 in, I get 3 to the 1 is 3 times 4 is 12. Now I'm going to test 2. 3 squared is 9 times 4, 36. Yay. Okay, let's look at the next one. The next one's a little bit harder. I don't know if you can tell what it's doing each time. What is it doing? I love that you said multiplying by 1/4, because you're right. It is also dividing by 4, but we should think of this in terms of multiplication. So it's multiplying by 1/4, okay? And then its initial value happens at right here. X is 0. So we would write f of x equals 8 times 1/4 to the x. And then test your points in there, okay? The book teaches it a little bit differently. They actually plug in a value for x and y and solve. But I think that doing it that way is just as easy, maybe a little easier. All right, so that was part A. Let's move on to part B now. Part B, we're going to talk about growth and decay. And you spent an entire chapter on this stuff last year in Algebra 2, so hopefully you remember it pretty well. Okay, so here we go. Let's do both. So let's say that we have f of x equals a times b to the x. A times b to the x. Now, we're going to have either exponential growth or we're going to have exponential decay. Okay, so let's go ahead and talk about each of those. So for growth, first of all, a is bigger than 0, and for growth, b would be greater than 1. Okay? B is your growth factor. Growth factor. And if it's bigger than 1, then that means that you're going to get more of something each time. And so the basic growth graph looks like this. You have this point right here, which is the point 0, 1. When x is 0, y is 1. Your very basic parent function. And it's going to go right along. There's an asymptote right there, and it's going to go right along, and then it's going to shoot up exponentially. I don't really like that very much. Goes right along here, and then it starts to increase very rapidly. And maybe you've heard someone say, oh, it was increasing exponentially. You kind of know what that means. It means that it increases rapidly, with rapid growth. And there's an asymptote right here at y equals 0. Okay, and that's your parent function. Now, decay is not going to be a base that's negative. We think, oh, it's decay, so it's negative. No, decay is actually, b is between 0 and 1. I don't know if you remember that from last year. Maybe not, and that's okay. And then here, b is called your decay factor. It's your decay factor. And so exponential decay will look like this. You're going down. And it never actually reaches 0 because there is an asymptote there, also at y equals 0. So for growth and decay, let's talk about the domain and range because they're the same for both. The domain, hold on. Let's go back to this color. Domain for both of these, for growth and decay, the domain are the x values. Now if you look at the graph, the x values range from all the negatives to all the positives no matter what. So the domain would be all real numbers. The range though, the range is going to be the same for both, but it's not all real numbers. The range is going to be, now you see there's an asymptote at y equals 0, so the range will be y is greater than 0. All the stuff above 0. Okay? And that's going to change if we flip it or move it or all that stuff, but the basic parent function starts like this. Also, this graph is continuous. These functions are continuous, growth and decay. There's no breaks in the graph. And they are also one-to-one. All right, so let's do one. Are you ready? Number 2. 2 or 3? 2? 3? 4? 4. 4. Where have I been? Number 4. All right, here we go. We're going to have the function y equals 10 times 1/2 to the x. We're going to do a bunch of stuff, quite a few. First thing we're going to do is we're going to say whether this is growth or decay. We'll circle one of those. We will also find the domain and the range. We're going to graph this. And I'm going to add one more thing. We're going to find the limit as x goes out to infinity for this graph. Ooh, and let's do the other way, negative infinity too. As x goes out to negative infinity for this graph. And I call it y, the graph of y, because that's what our function is called. Okay, so let's do it. Here we go. First of all, is this growth or decay? Decay. You can tell because this factor right here is 1/2, so it's decaying. We could even say that that's half-life. Well, not really quite half-life. We are going to do some half-life problems. Remember that? So that would be decay. Domain is going to be all real numbers. Let's go ahead and graph this to find the range. I mean, the range isn't going to change because it's not shifted up or down or anything. But let's graph this. To graph this, you can pick a couple of points and just plot them. So for example, when x is 0, y is what? 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's its initial value. Okay, a lot of times we start at x equals 0 because x represents time. In this case, it's a little different, but yeah. And then at 1, you're going to go half as much, right? X equals 1, you go 1, 2, 3, 4, 5. And then at 2, you're at half of that, which is 2.5. At 3, you're half of that. Half, half, half. Keep taking half. You end up getting, try to go through some of the points. And there it is. And then don't forget to actually include the asymptote here. Okay, so there's the graph of it. All right, so the range would be y is greater than 0. And the range is going to stay y is greater than 0 unless you're shifting up or down. You're moving the whole thing, okay? Now let's talk about the limit. Let's do first the limit as x goes to infinity. And I'm going to write it in red because I want to show you on the graph. As we're taking this graph, and here we are. We're going to walk on it, right? We're walking along. we're going to take it out to infinity. What is the y value getting closer and closer and closer to? 0. Yes, we learned that with asymptotes 2 last chapter. Okay, let's go the other way now. As x goes to negative infinity, we're going to walk this way on our graph towards negative infinity. Our graph is going where? Positive infinity. It's going all the way up to positive infinity. Okay, so that's the limits. You'll have questions on those. Okay. Now let's do some shifting of the graphs, okay? So we're on part C now. We're about halfway done. And let's do graphs by hand. Graphs by hand. Yes, no calculator on this. Your calculators could graph them, but we're not going to let them. So let's say that you start with basic y equals a times b to the x, okay? A is going to be kind of like the stretch of it. If you decide to do something like this, let's say your thing changes to y equals a times b to the x, let's do minus h. The book doesn't really teach it this way, but I think this will be helpful because you've done this so many times. X minus h plus k in a way like that. Okay? You know what that does, right? You know that this up here is going to shift our graph left or right the opposite way. Left or right. And then this right here, this plus k, is going to shift our graph up or down. Now, shifting the graph left or right or up or down is not going to change the domain at all. The domain remains all real numbers. Shifting the graph left or right doesn't change the range at all. As soon as you have a plus k or a minus k on the end, that will change your range. That's the only time the range changes, okay? Also, a negative x will flip it over the y-axis, and then a negative out front flips it over the x-axis. And we did those when we did shifting. So let's do one. Number 5? Number 5. Yeah. Oh, yeah. Yes. So if you have a negative out front like this, that will shift it over the x-axis. It shifts it that way. And if you have a times b to the negative x, that's going to be exponential decay. It changes from growth to decay. That shifts it, reflects it, not shifts it, reflects it over the y-axis. There you go. Probably should have written all that down too. All right, I'll let you catch up a minute. Drink more coffee. I hope we can finish here. Okay, here we go. Number 5. Let's graph y equals 2 to the x plus 1 minus 3. Okay. With this, I like to just kind of graph the basic parent function. In this case, the parent function would be y equals 2 to the x with an initial value of 1. Okay, it's like 1 times 2 to the x. So here's my parent function. It would go through 0, 1, and then it's doubling. So at 1 I get 2, at 2 I get 4, and it's just increasing very quickly. So I'm not going to actually draw the whole thing in. I'm just going to draw like kind of the shape of it. And then the asymptote is at y equals 0. Okay, so that's your basic parent function. Now this parent function, I'm now shifting it. I'm going to move it 1 to the left and 3 down. Now look what point I'm moving. Most of the time when we've shifted things, we start at the origin and we move it, right? Like a parabola goes through the origin, basic parent function. A cubic goes through the origin, we move it. This does not go through the origin, okay? I'm shifting from the point 0, 1. And I'm going to shift it 1 to the left and 3 down. So I'm going to go 1 to the left, that's over here, and down 1, 2, 3, and that's where this point is going to be. That's in blue both times, okay? Also, this asymptote, I'm shifting 1 to the left, which doesn't matter, but I'm shifting that down 3. Okay? 1, 2, 3. So there's my new asymptote. Make sure you shift the asymptote also. And then you know you got it. This right here was the point 1, 2. So I can graph this as, it was 1, 2, right? Yeah. So over 1, up 2. Does it go through the origin? 0. No, it goes through -1. It goes right here. All right, so we're going to go like this, and there you go. Now, once again, if you ever get stuck with the shifting, just plug in some numbers for x and try and figure it out. You know, there's always a way. I know that's why a lot of you guys like 20 extra minutes on your test, because you could probably figure it out if you were given time. But the shifting's really quick. You go to the left, down 3, draw your graph. Now let's talk about domain and range here, because a little bit's changed. The domain hasn't, like I said. The domain's going to be always all real numbers. Because x, there's no restrictions on x for exponential functions. You can plug in negatives and fractions and decimals and anything you want to in. But the range is a little bit different. In this case, the range is now, do you see where my asymptote is? It's at -3, right? So it's everything above that. So my range is, and you can write it like this if you want to. You can also write -3 to infinity. Don't include -3. That's an asymptote. It won't touch that line. All right, how about our good old friend? I don't know if you remember this guy. How about E? Do you remember E?
Yep.
Okay. So E is an irrational number. If you go to your calculator and you ask your calculator, what's E? I mean, it's not like Siri or anything. You can't just, you could do E to the 1, and it's 2.71828. It looks like it repeats on your calculator, but it doesn't. Okay? This is an irrational number. It cannot be written as a fraction. There's fractions that are close to it, but it cannot be written as a fraction ever. Like pi. They used to think pi was 22/7. 22/7 is pretty darn close. Look at that. 3.14285. Ooh, 3.141. See, it's really close. But pi is not a fraction, and neither is E. They're both irrational numbers. So sometimes they'll throw in an E as the base, like they'll have you graph y equals e to the x. It's just going to look like an exponential function, just a regular one. I don't really focus too much on this, because we can graph those on our calculator too. But if you plug in x is 0, you get e to the 0, which is still 1. And then if you plug in x is 1, you get, instead of 2, like the last one was doubling, it's a little bit over 2. It's 2.78. But it's the same graph, though. Ew. Like that. Okay? Just wanted to make sure you knew that. All right, let's do the last thing. I know it's a lot for one day. Letter D. And this one we can do on our calculator. So get your calculator out. These are called logistic functions. Logistic. They don't have to do anything with logs, though. You're like, oh, okay, we're going to graph some logs. Nope. Logistic function looks like this. You're going to have an asymptote through y equals 0. And then you're going to have another asymptote up top through y equals some number. I'll call it b. Okay? And then your logistic is going to look like this. It's going to look like it's exponential. See how it's rising exponentially? But then it tapers off. We had a problem like that. It was about bears and their population. Do you remember that? So it's rising exponentially, but then it just kind of, fizzles out. All right, so let's do, I have maybe one of these. Number 6. I think we have time for one more. Suppose that f of x is equal to 8 over 1 plus 3 times 0.7 to the x. Pretty gross, huh? You can't simplify that at all. You can't add the 1 and the 3. You can't multiply the 3 and the 0.7. Okay? And what we're going to do is we're going to graph this on our calculator. You can always graph logistics on your calculator. I won't make you graph those by hand. So graph this on your calculator, and then we're going to find some things. We're going to find the y-intercept. We're going to find the horizontal asymptotes. And we're going to sketch a nice smooth graph of this. Okay? So let me show you on the calculator how to actually input this in correctly, because these get a little tricky. When you go to your calculator, you're going to go 8 divided by parentheses. You got to put parentheses around the entire bottom, okay? And then it'll be 1 plus 3 times 0.7. That's the only tricky part, because your calculator knows correct order of operations. You don't need to put a bunch of parentheses down there. It knows it. To the x power, and then make sure to close your parentheses off, okay? And let's just hit zoom 6 and find out what this thing looks like. There it goes. It looks exponential until it doesn't, right? And let's look a little bit farther out on the x. Let's change our window to maybe an x max of 20, and then we can see it a little bit better. So it's exponential, and then it just kind of, you know, tapers off, okay? So let's go ahead and draw this graph in. Here's my horizontal asymptote. Ooh, if you ever want to figure out what the other horizontal asymptote at the top is, you can hit trace and take it out as far as you want to. That takes a while. You can also go to the table and go out the x's as far as you want to. What do you think it is? Oh, it told you. It actually doesn't equal 8 there. Your calculator is wrong. But see this number up top? That's going to be the other horizontal asymptote. So you have a horizontal asymptote at y equals 8 and another one at y equals 0. What was the y-intercept? Hit trace, plug in x is 0. I got 2. 2. My y-intercept is 2. I can graph that. And then this is what it looks like. It goes like this. Okay? So my horizontal asymptotes are at y equals 0 and y equals 8. And then they might ask you this one last question. Let's see if you can figure it out. What's the limit as x goes to infinity for f of x? And what's the limit as x goes to negative infinity for f of x? And I know that limits are, they're like a weird concept because, you know, you haven't done them too much. You will at the end of the year, and you'll be really good at them by then. But let's jump on our graph, and let's follow this graph out. See, this is x goes to infinity, and this over here goes to negative infinity. X is going to negative infinity. And the limit is, what is my y value getting closer and closer to? So as I'm going out to infinity, what's my y's what are they getting closer and closer to? 8. Ooh, I don't want to do that in red. 8, yes. As I'm going out to infinity. And then what about negative infinity? 0. And that's what asymptotes are as you go out to infinity. Okay, that was